Okay, let's take a look at this reaction. Here we've got nitric oxide being produced by the reaction of ammonia and oxygen. And we've been asked to calculate the mass of NO, the nitric oxide produced from this reaction. So if we take a look at the mass which we've been given for the NH3, which is 24.4 grams, that mass, as we've also been told that the oxygen which it reacts with is in excess, right? What's the implication there? Well, the implication I'm going to infer from that is the fact that we can effectively understand that the amount of nitric oxide produced, the H2O produced, etc., is going to be primarily limited by the mass of NH3. Effectively, the NH3 is the limiting reagent in this reaction rather than the oxygen. And therefore, the mass of NH3 that reacts becomes very valuable information for trying to effectively work out the mass of the nitric oxide that was produced. Okay, so looking at the nitric oxide, we've been asked to calculate the mass, right? Now, if you refer to the equation that links the mass, the molar mass, and the number of moles, as we recorded, that would be the mass would be equal to the number of moles multiplied by the molar mass, mR, right? And in this case, for nitric oxide, the mR, we could work this out from the periodic table. However, for the number of moles, it would be less straightforward, and we're going to explore how can we work that out. And then obviously once we work it out, we're going to then go ahead and try and just plug the values in to solve this equation. So for the number of moles, in terms of the amount of substance, it's not necessarily easy to work it out directly. But what we can do is we can work out the amount of substance, the number of moles for the NH3. Because as you can see, the formula for the ammonia, we have the formula, and we can use that in combination with the mass to work out the number of moles. Of course, what we'd need to do with the formula is work out the molar mass from a periodic table. This way we can use this equation, but rearranged. So if you do rearrange this, so for the mass equals number of moles times molar mass, divide both sides by the molar mass. This side, this would obviously cancel, and then we'd get simply put that the number of moles is equal to the mass divided by the molar mass, right? So we're going to go ahead and find that out from the periodic table. We already know that this, for the ammonia at least, is going to be 24.4 grams, right? Okay, so for ammonia, NH3, what's going to be the molar mass? Well, you've got nitrogen here, right? Nitrogen, and you've got hydrogen. So nitrogen, you can see it's got a relative atomic mass of 14. So that's going to be for the N. So this is mR of NH3. So for the N, it's going to be 14. And this would, because the coefficient with associated with the nitrogen is 1, it would be 14 times 1. But it's kind of redundant because 14 times 1 is 14, right? So I'm just going to write 14 there, plus, and then that, with the hydrogen side, it's going to be the relative atomic mass of hydrogen, so that's 1 multiplied by the coefficient for that, which is going to be 3, right? So plus 1 times 3, okay? And of course, when we calculate that, that is going to give us 17, okay? And that's going to be in grams per mole, right? So what we can do now is effectively use that value 17, because we already had worked out some of this. So this is going to be 17, right? So therefore the number of moles is equal to 24.4 divided by 17. So I would invite you to have a go, work that out, see what you get. If you do that, what you should find is you get 1.4352941. That's going to be in moles. Okay, so if we refer back to the original balanced equation which we have here, we need to look at the molar ratio, right? So effectively, the number of moles of NH3 compared to, as a ratio, compared to the number of moles of the nitric oxide, right? So if we look here, what do we have? We have 4 moles of NH3. For every 4 moles of NH3, we get 4 moles of nitric oxide, okay? So we can write 4 to 4. That's the ratio. That's what the balanced equation tells us. Now, as you can see, both of these values here are divisible by 4. So I'm going to divide them by 4. And if I do that, the ratio I get is 1 to 1. Right? And what does this tell us about the number of moles of nitric oxide? Well, this is what it tells us. Right? It tells us that the number of moles of nitric oxide is the same as the number of moles of ammonia, because it's a 1 to 1. You see, it's a 1 to 1 ratio. But that also tells us something else, because we've already worked out the number of moles of the ammonia, right? So therefore the number of moles of nitric oxide is simply the number of moles of the ammonia. And because we now have that value, all we simply need to do when we consider that equation again, which was that mass is equal to number of moles times molar mass. Remember, what we've been asked to work out here is the mass of nitric oxide that was produced. This is simply equal to the number of moles multiplied by the molar mass, which we have this down here, and this we can work it out effectively from the periodic table. So let's go ahead and do that. So this is going to be MR of NO, right? Now in both cases, as you can see here, the coefficients are 1, so I'm not going to write multiplied by anything, it's just 1. But you can understand what's implied is that I have multiplied them by 1, and the 1 has produced, itself basically. So in this case, for the nitrogen, we've got 14, right? 14. So that's going to be 14. And as I said, implicitly it's going to be 14 times 1, okay? But I'm not going to write the 1. Plus, and then for the oxygen, it's going to be 16, right? 16 times 1 implicitly. But again, I'm not going to write the 1, right? And if you add that up, that's going to give you 30, right? Grams per mole. Okay, so if we take that 30 So as you can see, the MR is going to be 30. So the mass of NO here is going to be the MR 30 multiplied by the number of moles so I didn't include the units of the molar mass. I mean, we know what that is, as grams per mole. So just to be consistent, I'm not going to include the units for the moles at this stage, but we know that's referring to the moles. But then that's gonna if you have a go work out what that's gonna be, but you should find that you get 43.05823, and that's gonna be in grams, right? So we have a mass figure now, corresponding with the nitric oxide. However, if we do refer back to the question again, it says give your answer to a maximum of 2 decimal places. So we do have to conform to that in this case. What should I say? Adhere to that, but you know, same thing. That's going to be if we round that, so 43.05, we need to round that up, right? So 43.0, round that up, it's going to be 6 grams, right, to 2 decimal places. Okay, so that's effectively going to be, in this case, the mass of NO that was produced.